Hello, everybody. Let's talk about section 12.4, volume of prisms and cylinders. So we're halfway through chapter 12, and we've done surface area and lateral area. And now we're going to start talking about volume. So surface area and lateral area was the outside of a figure. If you're going to wrap a prism, wrap a gift, how much wrapping paper do you need? Well, volume is the measure of the amount of space that a figure encloses, how much fits inside that figure. And we always measure it in cubic units, so centimeters to the third, or cubic centimeters, or if you've ever heard on Dr. Show, cc's, that's cubic centimeters. That's talking about volume. We've got two formulas. We're going to just talk about prisms and cylinders today. So prisms, I think the formulas for volume are easier. So the volume of a prism is the capital B times H. We all know that capital B stands for the area of the base. This should be a capital B right here. And we all know that a capital letter signifies a potential side problem. If we're finding the area of the base of a prism, it could lead to a snap problem. It could lead to just base times height. It could be a triangle, so base times height divided by 2. H is the height of the prism. Remember, we talked about with surface area, height is the distance between the bases. The volume of a cylinder is pi r squared h. Pi r squared is the area of the circle base multiplied by the height of the cylinder, or the distance between the circle bases. So it's really the same formula, only just like we found with surface area, cylinders are easier. There's no side problems because pi r squared h is built into that problem. So let's do a couple practice problems. These are our two formulas for the section. This is it. There's nothing else that we need to talk about. Just do some little sneaky problems. So let's talk about problem number 1. First of all, it's a prism, right? What kind of prism is that? On the quiz, if I asked you to name that solid, that polyhedron, you would tell me that that was a triangular prism, which means what are the bases? Triangles, right? So when we do volume equals area of the base times the height, we've got to find the area of the base. Side problem, heads up. So would you agree that if this is 17, then this one must be 17? All the other lateral edges must be 13, but it's labeled with an A. We're missing that value. There's nothing there. So how are we going to find that? Because it looks to me like this is our triangular base closest to us. So that's what we're going to have to find the area of. Notice there's no perimeter problems in this, so we don't need to know the perimeter. So area of a triangle equals the base times the height over 2. Do we know the base of that triangle? Ignore the prism, just look at the triangle. We don't, right? Does everybody see Pythag happening here? And we're looking for a leg or a hypotenuse. That A, this A that's labeled right here, is a leg. Oops, that should be equal 17 squared. Do the math on the side real quick. Tell me what you got. I ended up with a 15. So the area of my triangle is going to be 15 times 8 divided by 2, because remember the base and the height are always perpendicular to each other, so I'm looking at that right angle. So that looks to me like it's probably 60. So now I'm ready to go over to my volume formula. Area of the base is 60. What's the height of that triangular prism? Again, this is a laying down height. You're still the same height if you're laying in bed or if you're standing up. The distance between the two triangle bases looks like 13 to me. So the volume is going to be 780 cubic centimeters, or centimeters cubed. Let's do this second problem. Obviously, what kind of solid do I have here? It's a cylinder. Is a cylinder a polyhedron? Hopefully you know why I'm asking that question. It's not a polyhedron because it does not have flat lateral faces. It's got circles, so it's got to have all polygon sides. So this one, if we're going to do the volume of this cylinder, our formula tells us that we're going to do pi r squared h, or the area of the base times the h. So, do you sense a side problem coming on? This is a right cylinder. If I draw this in, would you agree that's the diameter? And I have to have a right angle here. So we do have a side problem for this cylinder. We've got to find the diameter so we can find the radius because we need to know the radius and the height. So Pythag this time, I'm looking at a d squared plus a 15 squared equals 17 squared. Do the math, let me know, but I think that diameter is going to come out to 8. So what are we putting in for the radius then? And what's the height of that cylinder, or the distance between my circle bases? So I'm looking at a pi times 4 squared times the height 15. When I do that math, round to the nearest tenth, I got a 754.0 cubic feet. I got confused for a second. It's cubic because we're thinking how many cubes actually fit inside there. So if we had cubes that were 1 foot on each side, we could fit 754 of them inside that very large cylinder. Cavalari's principle. It says it doesn't matter where you're looking at the area of the base, because remember our formula is volume equals area of the base times the height. If the height stays the same for any kind of solid, and the area of the base is the same no matter where we are, if we're down on the bottom, up on the top, somewhere in the middle, then they have the same volume because we'd be multiplying the same value for the area of the base and the same value for the height. So in other words, we can find the volume of oblique prisms and cylinders. So now we can deal with those slanted cylinders and prisms instead of just right ones with nice, neat angles. So let's do problem 3 and 5, I think. So 3. I put that little stack of quarters over there on the side so that you could see it doesn't matter, right? The quarter's still the same size no matter if I slant the pile or leave it straight up and down. So my volumes will stay the same. So volume for a cylinder, area of the base times the height. So what is the radius? And what is the height of that stack? Use an altitude, not an axis. Make sure you use the height. The distance between the bases, you must have a right angle. So that would be a 9 for the height of that stack of quarters or whatever it is. So the distance from the lowest to the highest point. When I do that math, I end up with a rounded number, 452.4. Cubic yards. Alrighty, last but not least, let's look at a prism. The weight of water is 0.036 pounds times the volume of water in cubic inches. How many pounds of water would fit into a rectangular child's pool that is 12 inches deep, 3 feet wide, and 4 feet long? Notice we're going to multiply 0.036 times the volume in cubic inches. So what do you see about my diagram or my units right off the bat? I can find the volume of a child's pool, right? And I can use that value to find out the weight of the water in it. but I have to watch out for these units. It's 12 inches tall. We could turn that into a foot if we wanted, but this tells me that I probably want to turn it all into inches. So what's my 4 feet going to be in inches? Hopefully everybody knows there's 12 feet or 12 inches in every foot. So 3 feet. All this means is that when we find the value of the volume, it's going to be a large number. So volume equals area of the base times the height. Well, the area of the base, would you agree in a child's pool that this bottom part down here is going to probably be the base, right? My nice coloring job. So the area of the base is going to be 48 times 36, base times height, which will be equal to, gosh, 1728 square inches. Well, now I'm going to put that 1728 square inches into here. And what is the height of that child's pool? 12 inches. Sometimes people with prisms skip over the area of the base times the height, and they just do length times width times height, which is actually the same thing because length times width is the area of the base. So I know it's a little shortcut. If you're going to do it that way, make sure you show me in your work that you're going to show that that's what you're showing, that that's what you're doing. So when I do this, I end up with 20,736 cubic inches. That's a lot of water. That's a lot of cubic inches of water that we can put in there. But it does want to find out how many pounds of water would fit into that. How heavy would it be? Well, if the weight of water is 0.036 pounds times the volume, and I just found that the volume was 20,736 cubic inches, I'm just going to multiply that. And when I do that, that's going to tell me how many pounds of water are going to fit in that little 3 foot by 4 foot by 1 foot tall pool. So I have, this would be tough to move once you fill this guy up. Do the math, and I had 746.5 pounds of water in that pool. You should probably move it before you fill it, huh? I'd have a tough time moving that. So it was a practice in finding the volume, but then using that to find the weight. So, oh, hello. Good thing it's Classic Joke Wednesday. What do you call it when your Nana's on speed dial? Don't be a shouter-outer. I know how you guys are. This is a good one. You're going to like this. When your grandmother is on speed dial, you call it Instagram. Funny one, huh? So your homework / classwork is on page 866. It's all evens all day, so 10 through 20 and then 28 to 34. 10 to 20 are just some basic problems figuring out the volume. 28 to 34 make you think a little bit more, so hopefully you can think working backwards, that kind of thing. We will discuss the quiz when I get back, and Tuesday I'm looking at a chapter 12 test. We'll finish the rest of the notes for this chapter 12 this week, and then we'll get on with reviewing on Monday and testing on Tuesday. Have a great day. We'll see you guys next time around.